Okay, in this lecture, I'm going to teach you how to handle some of those integrals that we began discussing. In fact, there are three different types of integrals of real valued functions that we will be able to handle by means of the method of residues. So the first type, so these are the real valued integrals. The first type is the one we've dealt with already, where you have something like the type, say, x squared over x to the 6th plus 1 dx minus infinity to plus infinity. In this case here, we simply define the poles, and then we hit this with the residue theorem. Residue theorem, it's just 2 pi I, the residue of f of z at whatever zk, all points that are on the poles that are discovered. Of course, the requirement here was that you have n of x, a numerator divided by a denominator, and this only works provided that the degree of n is less than the degree of d plus 2. So the degree of n must be 2 less than the degree of d. Let's put it this way, it's a bit clumsy. Otherwise, 2 goes there, 2 plus the degree of n is less than the degree of d. So that's why something like x squared of x to the 6 plus 1 works, and you can hit that with the residue theorem. Then you also have all complex poles. There are no real poles or simple poles that are available in this kind of problem. So this kind of problem is handled by means of this theorem if it has those properties. Now, in this discussion of the proof, which we didn't discuss in class, the proof hinges on what we call the theorem due to Cauchy. It was a theorem which had the result that if you take a contour like that, a circle, semicircle, CR. In fact, we call this Jordan's theorem. Let's call it Jordan's theorem. So according to Jordan's theorem, the integral of f of z e to the I k z dz minus infinity to plus infinity is 0. Sorry, let's not have these limits. We're talking here simply on the CR, the semicircle. Notice this part here. So that's a very important part there of the theorem, Jordan's theorem. And here, of course, k is more than 0 is demanded. So when this theorem is being worked on in the proof, we need this degree of the numerator to be 2 less than the degree of the denominator. So that's the reason why we need it there. All right, we've dealt those kind of problems in class. Let's take another kind of integrals. So you have the Fourier type. Fourier type, where you have, for example, the integral of x sine x over, let's say, x squared plus 9. Again, at the bottom you've got complex valued roots, and on the top you've got sine x, maybe sine 2x, 3x, whatever. So that makes it like a Fourier type. So you have here a numerator and a denominator again. This time, the only requirement is that the degree of the numerator must be just less than the degree of the denominator. Degree of n is just less than the degree of d. That is all. You don't need it to be 2 less. It just has to be less than the degree of d. Now, the reason for that is because you want convergence. You want convergence to take place, and that's when you can get. This allows us to interchange integral with imaginary. When functions are convergent, then you may be able to change these two here, and then you'll get away with the calculation. So the method in this case here is to use the result e to the I kx dx equals to cos kx dx plus I integral sine kx dx. Okay, so you can have the limits from minus infinity to plus infinity, the same limits throughout. Now it is perfectly legal to say that if you want to work out the integral of, say, f of x cos kx dx minus infinity to plus infinity, then that will be the same as the integral of minus infinity to plus infinity of f of x e to the I kx dx. And you can take the real part of that. Or if you want to work out the integral of f of x sine kx dx minus infinity to plus infinity, it's perfectly legal to take the imaginary part of the integral of f of x e to the I kx. There's no need to justify anything further here. This is perfectly legal as it stands because we're simply exploiting Euler's theorem. E to the I theta is cos theta plus I sine theta. So one can then calculate these integrals in that form there. And of course, you ask the question, why do we have to go from cos kx to e to the I kx? Why use e to the I kx? The answer is because in the proof of the residue theorem, because these calculations here will boil down to using the residue theorem eventually. In the proof of the residue theorem, we made use of Jordan's lemma. So Jordan's lemma tells us that if you have a semicircle there, CR, then the integral along CR of f of x e to the I kx dx is 0. That's the result that we have been using all the time. So therefore, we have to convert the sine kx to e to the I kx because this is when the theorem actually works, when you have e to the I kx. But now we can go back using real and imaginary parts to work out the cos and the sine parts separately. Fine, so we've dealt with some examples of that type in class. We're going to now look at some other types. Let me just add on some pages here. So let's have a look at some examples of the third type. And this will also now help us to investigate this idea of interchanging the imaginary part with the integral, under what circumstances it can be done. So the third type of integral is the type where you have a real pole. You have a real pole in D. So when you have a real pole in D, for example, if you have the integral of, say, sine dx over x into x squared plus 9 dx minus infinity to plus infinity. So now you have a real pole here. So it makes it difficult now to discuss the idea of convergence. Of course, again, you want the numerator to have to be a power that's lower than the denominator, because then you can virtually assure the convergence. So that's when you can perform some simplifications, which you otherwise can't do if you're dealing with divergent functions. But Cauchy came up with a neat trick. So he found a way to get past this here, and he defined what we call the principal value of the integral. And this is a more broader definition of the normal integral. So in his definition, it works like this. So suppose you have a point z0, which is exactly on the x-axis. Then now it's a real pole. And then you may have other unreal or complex valued poles there. You do your normal, surround that by means of a semicircle. Let's call that P. And the contour now, you perform the following. What you do is you surround Z0 by a semicircle of radius epsilon. So if you take any point on the semicircle, Z, it will be either Z0 plus epsilon e to the I phi, where phi is the angle. And the angle will be measured from pi up to 0. Why? Because if you follow the path here, you'll see you're going up there. So you're starting off from here at pi, and it's ending up there at 0. So it's going opposite. And then it's going this direction here towards b. Let's call this a and this b. So the principal value of the integral is defined as follows. Well, it's built up as follows. So we take, if you want to find the entire integral that we have here in the picture, the integral of f p dx plus the integral of, now let's take this side here. This point here is z0 minus epsilon. This point here is z0 plus epsilon. The radius is epsilon, if you recall. So we can go from z0 minus epsilon. Well, actually, we can go from a to z0 minus epsilon f dx. So let's use z here, since we're using z0. Plus, then we do the integral along this curve. Let's call that c epsilon of f dz. Plus, then the part from z0 up to b would be actually z0 plus epsilon up to b f dz. And so that covers it all now. And this here, by the residue theorem, should be 2 pi I residue of f of z, or z equals to zk. It doesn't matter how many you have. You can have as many as you want. Right? Okay, let's put the sum there. That's how it works. But you know that this part here is defined as the principal value. Principal value of f dz is defined as that integral from a to z0 minus epsilon plus the integral from z0 plus epsilon up to b. That's how it is defined. And we'll see now how this can be dealt with mathematically. It's actually very neat the way how she envisages how this will work. So let us now consider this integral along c epsilon. Let's talk about that for a moment. So recall that we call that z equals to z0 plus epsilon e to the I phi. And phi belongs to phi naught because of the direction of travel, this way to that way. From pi up to naught. Pi goes around to naught. So if you take dz, you will get derivative of z0, which is 0. It's epsilon I e to the I phi. And now, recall, if z0 is a simple pole, then actually you can write f of z in the shape g of z over z minus z0. And you can then say that the residue of f of z at z equals to z0 is actually g of z0. So now in this integral of f of z dz along c epsilon, you can write this as integral of. So on the top you got g of z, so it will be g of z0 plus epsilon e to the I phi. This was g of z, so it's g of z0 plus epsilon e to the I phi, divided by z minus z0, that's epsilon e to the I phi, times dz. What is dz? dz is epsilon I e to the I phi, d phi. There's a d phi missing there. Okay, let's now try to simplify this. So this will kill that, epsilon kills that. Oh, by the way, it's from pi to 0. So if I want to switch this around, and remember there's still a, a pi here, so I can make this an I, minus I, and change the limits from 0 to pi, g of z naught plus epsilon e to the I phi d phi. Now let epsilon go towards 0, become very small, make the radius very small. Then you'll get the integral of f dz along c epsilon will work out to minus I integral naught to pi g of z naught. So this part here is now 0. Epsilon is 0, d phi. So now you will observe that we may now take out the g of z naught because the integral is for d phi. So you can see this is one of the reasons why we can interchange imaginary with integral, because of the fact that g of z naught has got nothing to do with phi. We could not. So if we just carry on a bit with this, it's minus I g of z naught, and this here, the integral of 1, d phi is phi, from naught to pi. Effectively, you get minus I pi g of z naught. But if you look above, you will see that minus I pi g of z naught is actually the residue of f of z at the point z equals to z naught. So if we plug this now into the 4 integrals we had earlier, plug into the 4 integrals, actually now we can call it 3 because 1 is not the principal value. We'll get the integral along p of f of z dz plus the principal value, that was a 1 a to b of f of z dz. Recall it was from a to z naught minus epsilon and z naught plus epsilon up to b. But now we call that a principal value. Then we put this other one here, minus this integral along c epsilon. That will be minus I pi residue of f of z at z equals to z naught. And all of this is equal to 2 pi I residue of f of z at z equals to any zk. Effectively, we get the integral of f of z dz along p. That's not necessarily 0. So this is not applying Cauchy's or Jordan's lemma here because there's no e to the I kx. But you have here the principal value from a to b of f of z dz equal to 2 pi I residue of f of z at all the complex roots plus pi I residue of f of z at all the real roots, z equals to z naught. So in other words, the principal value of f of z from a to b dz is just pi I residue of f of z equals to z naught. And this will now prove to be very useful in carrying out those calculations. This allows us to interchange integral with limit, or with imaginary or real. Now it will become legal for us to do this. I'll show you a few examples in a short while.